Although I am sad. Because this is our last day of lecture, we are not going to do justice on flip-flops. It's the most fun and whimsical term in all of electrical engineering, and we're just going to like barely grace over it as we move onward. Super sad. Oh well. All right, what's the answer to this? E is equal to everybody get that? Did you derive it yourself or? It's terrible. So what is the answer to this? What'd you get, Jonathan?
I don't think it's very right. I got A, B, D naught plus D naught, C naught, D.
Hey, wait, hold on. What's the first term?
A, B, D naught.
A, B, D naught. A, B, D naught represents
I don't remember first.
these two.
I think so.
Yep.
I think it does.
Okay, so you got these two? All right, so what's the second term?
B naught, C naught, D.
C naught, D. Okay, so here we've got B naught is these two. C naught is this one. D, so that would be these two.
Yeah.
Okay, what's the next term?
B naught, D naught.
B naught, D naught. So that would represent B naught is these two, and D naught is these two. So that would actually represent all four of these, which is not true. So
I got confused on how to translate the ones that are not right next to each other.
that one you're going to end up having four terms in it. So here, this is B naught, D naught, yes, but this is also A naught, C. So we could just write this as A naught, B naught, C, D naught. Okay? And that specifically identifies this one square.
And then my fourth term also only had two. So
Okay, well, what is that? What is the last term? A naught, B, C, D. Because it's B, A naught, B, C, D, and that identifies that one. That is the right answer. So, you'll probably have a Carnot map on your quiz. Just FYI. All right. So, let's talk about Boolean algebra, because once we have equations like this that we can generate from truth tables now, we take truth tables, turn them into Carnot maps. Take our Carnot maps, we can generate Boolean algebra statements. We can take these Boolean algebra statements and sometimes we can even shorten these down a little bit. But what we're going to be looking at right now is something called De Morgan's laws. So, let's do a recap on Boolean algebra. Boolean algebra. Okay? The idea of Boolean algebra is we really have two terms. We have multiplication, which is, ironically, it's like the same thing as division, so they get lumped together. But this is, anytime you have multiplication, you have an AND gate. Anytime you have addition, you have an OR gate. And anytime you have a 0, that's represented by a NOT gate. Okay? So an invert, I guess, would be the better way to put that. Okay, so we have our three different functions. So if I were to write this term right here, this is A and B and D naught, or B naught and C naught and D, or A naught and B naught and C and D naught, or A naught and B and C and D. Okay? That's ultimately the progression. This can all be put into one single AND gate, as can this, as can this, as can this. This requires one inversion. This requires two inversions. This requires two inversions. This requires one inversion. And then we plug the outputs of all of these into a single AND gate, an OR gate. And that's our answer. Okay? This way is called a sum of products. Actually, I have to go backward in the chapter. Problem is I bounced around a little bit in chapter 7 because I'm trying to teach it the way that makes the most sense to me. This is called a sum of products. And the whole reason why it's called a sum of products is because we sum products. There's nothing revolutionary there. The idea of a sum of products is that you have a bunch of AND gates and you dump them all into an OR gate. Well, it turns out you can do it the other way around, where you have a bunch of OR gates and you dump them all into an AND gate, which that is referred to as a product of sums. Okay? And it is the exact opposite. So making a sum of products, this is pretty simple. Right? We can do this with just some Carnot maps, truth tables. This one's not too bad. But how do we get what is called a product of sums? Here, this is where you have a bunch of OR statements. Dumped into an AND gate. How do we get that? Well, there is no way you're going to know this off the top of your head unless you did the reading and you actually know this like super well. The way that we have to do this is something that's referred to as De Morgan's laws. Which I have to find that in my book because I do not have them memorized. Where are you, De Morgan's laws? I went too far. Okay, De Morgan's laws are twofold. There are two of them. Are given by A and B and C is equal to A naught and B naught and C naught not. Well, that's fun. On the other side of it, A or B or C is equal to A naught, B naught, C naught, not. That's why I don't expect you to memorize that one. That's why I don't have it memorized. What the heck? What is this weird madness? Well, here's what this means. Okay, anytime I have a sum, I can convert it into a product. Anytime I have a product, I can convert it into a sum. Okay? So if you look at it, let's look at the truth tables real quick. Okay? Let's say I just have two variables here, A and B. Okay? And let's say I have A and B and B both go into an AND gate and produce C. The truth table is 0, 0, 0, 1, 1, 0, 1, 1. The output here, C is only 1 if A and B are true. What De Morgan's laws say is that this is also true if we take the sum of where A naught and B naught, A naught or B naught are, and then take the inverse of that. So what that means is if we do this circuit where we then take it into an inverter and then we plug it into an OR gate, and then out of that OR gate we make it a NOR gate, we should get the same answer. That's psycho. All right, so let's draw the truth table for this. A, B, C. Okay, we got 0, 0, 0, 1, 1, 0, 1, 1. Here, if A comes in and A is on, then this is off. If B is on, then this is off. If both A and B are off, then this is on. So the only way to turn this on is if both A and B are off, and the only way both A and B can be off is if both A and B are on. Which means we end up with the exact same truth table. It's crazy. Feel free to prove that to yourself. Let's go ahead and take this case right here. A is off, B is on. We take A off. What is this? What is the value of this if A is off? This is equal to 0. This is equal to 1. So if A is off, then the output of this is on. If B is on, what is the output of this? That's off. Okay? Now, we plug this into a NOR gate. We have 1 on, 1 off. What's going to be the output of this? Cadence says off. I mean, I told you that in the truth table, but it is off, and it's off because the NOR gate is only on if both of the inputs are off. So De Morgan's laws, I mean, you can feel free to go through the other one in the same way, where you have A, B, C, sure, D. We'll make D just for funsies. Plug it into an OR gate, okay, and have it produce E. Here, the truth table for this, A, B, C, D, E. I'm not going to draw out the whole truth table because you have 0, 0, 0, 0 is equal to 0, and then everything else is 1. Okay? Or we can take this one, which is if we take A, B, C, and D, we invert all of them. And then we plug it into a NAND gate. We get E. That's what the equivalent circuit is. And all of this says is that no matter what the inputs are, we're going to get the same truth table for this system as we get for this system. That's all it is. We've already shown today that there are multiple ways of getting the same truth table using different circuit configurations. There is an infinite number of circuit configurations you could come up with. Most of them are wastes of your time. You could run into an equivalence gate forever, where you just plug in A is equal to A constantly. You could have that go infinity. It doesn't do you any benefit. But you can do that because you have an infinite number of options. Okay? So De Morgan's laws are here to try to help simplify some of the Boolean algebra. And the idea here is if we can simplify the Boolean algebra, we can take these same statements and we can make a more optimized digital system. That's the whole purpose of it. So anytime you see something where you're getting it and it's A not B not C, not. Anytime you get a system like this, guess what? You can plug it into here and reverse this. Or you can similarly use this one and say it is the reverse of A plus the reverse of B plus the reverse of C reversed. So here, that one would be equal to, if we use either of these cases, here we take the not and we slide it over here because we don't have a not here. These are equal to the same. It's equal to a NOR gate of A plus B plus C in a NOR gate. Okay? And this can be useful if you just have systems of things where things are weird. If this would have been A not B not C, then we could also write this as A plus B plus C naught and put that in an OR gate. Those are equivalent now. Okay? And that's how De Morgan's laws work. You can NOR and not as you please. Any questions on this? Okay, let's make it a little bit more complex. I'm just going to jump in here and turn the knife a little. So first of all, I'm leaving these up because I don't even remember these. Let's take a product of sums and convert it into a sum of products. Actually, I told you my basketball career was over. Let me go get a better whiteboard marker. I have a bunch in my office. We don't have to live subjected to the tyranny of bad markers. Also, this shows up better on my live stream. All right, so we're going to take a product of sums. No, sorry. We're going to make a product of sums from a sum of products. Okay? That's all we're doing. So let's say we have E is equal to A, B naught, C naught, D, plus B, C naught, plus D naught. Okay? If we were to plug this directly into De Morgan's law, what is the equivalent product of sums? Well, first we got to start with terms. Here, we know that ABC is equal to A naught plus B naught plus C naught. So that means that A, B naught, C naught, D is equal to A naught plus B plus C plus D naught. And then we go ahead and plug that into a knot. So these are equal, plus B naught C is equal to B naught plus C. We put that into a knot. And then D is equal to D, not. That one can't be simplified. Because this D naught is equal to D not. Which that's just dumb. 2 knots equal a yes. 3 knots equal a no. Also, 3 knots is a fairly nice cruising speed for a boat. So, my parents said I'd never be a successful comedian. That's right, Mom. Sorry, Mom. Now I just gotta make sure I delete this video as soon as class is over. All right. Okay, so we've taken each of these products and turned them into sums. Now we're gonna take each of these sums and turn them into a product. Okay, because we're gonna use this exact same principle. A plus B plus C is equal to A naught, B naught, C naught, naught. Okay, so using this second principle, we then say E is equal to A naught plus B plus C plus D naught. We already had the knot on top of it. We draw a double knot because we want this knot tied well. And then we take that and we multiply it by B naught plus C naught. And we take another knot, we put that on top of it because we have to. And then we multiply it by D naught and we take that and put another knot on top of it. Well, that's gross. So, to recap, this term, we're going to call this term F, which means that if I take this and I just rewrite this, E is equal to F plus G plus D naught, which is now in this form, where F is this is G, and we have our D naught just hanging out there, just, not D'ing. We then multiply these each by each other. E is equal to FG D naught. We then take a knot and put it on top of them, and then we draw a knot over the top of all of them, which means I forgot that one knot that goes on top. If we expand this out, it is equal to this. Now we can simplify this a little bit because we have not. So what we end up with is E is equal to A naught plus B naught plus B plus C plus D naught times B naught plus C times D naught. And that is our product of sums. Okay, I'm going to do the same thing I did last time. I'm going to give you a problem, give you a break, and then we're going to come back and talk about flip-flops. Because I want to talk about flip-flops a lot. All right, so you have E is equal to A, B, C, D naught plus B naught, C plus A naught. This is written as a sum of products. I want you to write this as a product of sums. Okay. I will see all of you back here at 9:55, and we'll keep going.